Hello guys, and welcome to another mini presentation from the subject Principles of Computer Graphics and Image Processing. As the weeks passes and the semester goes further, we are getting to even more complex principles, and after last week where we are drawing only lines or curves, now we are getting to something serious. We are going to draw some 2D shapes. Well, obviously only 2D shapes, because we are going to draw them manually, and we are not going to draw 3D shapes by hand or by code. On the other hand, we are going to learn how to transform, or actually maybe move and animate these 2D objects with 2D animations or 2D transformations, and them you will be doing manually even in the 3D. So let's animate and also model. So what actually is a 2D shape? Well, it's very simple. It's only a polygon. We have some set of points that are connected by lines, and inside of these points we want to fill the pixels and have these pixels showing the polygon we want to show, or the 2D shape. Well, sure, we know how to draw points and the rasterized image and the display itself. We know how to draw lines between these points, even with the rasterized or even without rasterization somehow, by using Bezier curves, the vectorized lines. But the real problem actually comes not by drawing the lines, but by filling and painting this polygon. So what are we going to do now is to think about how should we paint the 2D shape. If we are going to draw it by filling the lines, sure, we can just think about it, just go through the X and search if we are inside or outside the polygon. But that could be quite difficult because we don't know where the polygon starts, where the polygon ends, and if we are just setting the flag like, okay, now we are inside the polygon, sure, now are we inside, are we outside, what's going to happen? Because we hit the outside of the polygon, and should we go further? Well, yeah, it's kind of difficult. So what is a very simple polygon, or the 2D shape, that we can definitely say that if you are inside or outside? And that is triangle. Because we start at one side of it, we always end up on the other side, and that is the final part of the triangle, final from the beginning to the end. So if you want to paint the polygon, the very simple thing is to just decompose it into simple triangles. So if we have some difficult polygon, even maybe concave or convex polygon, we just decompose into triangles and then paint the triangles. How to do it? Well, the last week you were trying to do some lerping or linear interpolation, so you know that that is quite the most simple way how to draw a Bezier line. But if we are not just selecting some points we want to draw, but we are painting every point between these interpolated lines, we can actually fill these triangles. So we are going between those two sides of a triangle, interpolating by the parameter t1, both of them with the same parameter, and then between them there will become two new points, x and z, x and epsilon, and by interpolating that this line with the parameter t2, we can draw the points of the line between each side. And by this we can draw a line, we can paint the whole triangle just using the correct t1 and t2, depending on the on the size of the polygon. So actually painting 2D shapes is not painting 2D polygons, but painting triangles at its simplest. And by painting triangles into these shapes, we can very simply imagine that even the 3D objects are not really some difficult multi-polygons. They are just created from simple triangles. And if we want to create a very difficult large object, we need many triangles. So that's why we are not doing it manually. But now we are thinking simple. I want to imagine and practice how to do it in OpenGL. Well, and to define them, how they actually work in the OpenGL and how should we implement them in on your weekly task. First, we imagine something simple, a rectangle with its 4 vertices that are placed in the coordinate system, and it's very simple to decompose a rectangle into 2 triangles. We have one triangle here and one triangle here. And actually in the OpenGL we have 2 structures defining every object. First is its vertices, as I said here. It's the position in the coordinate system. And then the indices for the triangles that are painting these images, these shapes. So what we do is actually we have in an array the vertices of the objects, and then we have to define how and which of these vertices are the actual triangles that should be painted. And again, the order of these indices, as you can see here, 0, 0, 1 is here, 2 is here, and then here. The order is really important, because the order of these images, of these indices, actually defines how is the triangle oriented. So the order of the indices is very important, and it's very similar to the right hand, because actually if you want the triangle to be facing to the camera, we have to use the right hand rule, but using this, and that's point. If you're using the indices in this way, it's going to be back facing, so we will not see these triangles in camera. You can use it, you can check it, you can swap the order. It's for your own good and your experiment. So again, we have to define the order, because if we define the order different way, the one triangle could be facing the camera, the other one could be facing the other way from the camera, and we need it to be facing to the camera with its normal, so we can see the actual image, the actual object, the shape. So now animations. What are animations? They're actually transformations in time, because we want to transform something, to move it somewhere, or to rotate it or something with it, to change its scale or shape. And if we're doing it in time, we're actually animating. And how to do it very easily and in computer graphics, we are using the power of the matrix to change the world. Well, literally, because we are using matrices and we are changing our world in the scene in the computer program. So what is the first important thing? We are using affine transformations that are actually combinations of linear transformations and translation. To use them and to be able to use them on points in 3D space or in 2D space. In 2D space we have points of only 2 coordinates, x and epsilon, but we need a third coordinate, so we can use the affine transformations, or actually the matrix transformations. So we are using the homogeneous or the projection space, and we need to convert it to the Euclidean space. Default value for the third coordinate should be 1, because now we see what is the conversion, and it's defining the W, or the value 1 is defining the distance between the TV projector and the screen. If we set it to 0, we set the point to the infinity. If this point or this coordinate increases, the screen moves away from the projector, so the image, the shape should be smaller and smaller. Also depends on the projection. Then, if you want to combine these transformations, we use matrix multiplication, and the final result of all these transformations is very dependent on the multiplication order. Well, if you use translation, rotation, shear, and scale in this order, it would be definitely different if you reverse it. You can try it, you will see. But the main thing is that you go from global to local. But yes, you can go here. Now we see there are samples of the transformation matrices. The first one is scale, then shear, rotation around its own axis, around actually the z-axis. In 3D there are variations of the rotation matrix, and then of course the translation. And as I was talking, it depends on the final animation. The transformation depends on the order of the matrix multiplication. And the simplest way how to explain it is that we are going from the most global transformation to the most local transformation. So if we want to downsize our shape and not to downsize the whole transformation, we do it first, and that's also on the most right side, and then we multiply it by other transformations. So maybe if you want to rotate around the arbitrary point, first we have to translate our we have to translate this point to the origin of the object, then rotate it by the selected angle around this position, and then translate it back. And it would seem that we had translated this object around the selected point. And animation, as I said, it's just a linear transformation of these matrices in the actual time. We know when we want to start, we know how long the animation should take, and we are just going by the parameter of how we should transform the first transformation matrix to the final transformation matrix. And that's it. We are getting to the fourth weekly task, which is obvious from the last few slides, and it is that you have to, not me, I had actually done it a few years ago, but you should draw a 2D polygon in OpenGL and encapsulate it, the implementation of its shape, into class shape. Why? Because it can be initialized multiple times. So you can create multiple objects in the scene, multiple of these exact objects. The thing is, you can change their transformation or the animation, and that is that object shape should contain parameters for setting the position, rotation, and scale. And you have to use them to compute the final transformation matrix of the model used for the view. now you don't know which objects, how they should look, or what animations, but all of this is in your Google Classroom as a specification. And now for the code. So we are in the code. So what today? First, as I said, you have to define the shape or the actual object. Well, as I said in the presentation, the object is defined by its vertices in the coordinate system, and then by the mesh or the actual indices of these triangles created by vertices. Well, you have to know, you have to define the triangle, which is actually defined as a face. It's here, and you have to define what is triangle defined of, well, and how we would address these triangles in the mesh. And as you know, there are indices, and the indices are just very simple type, so I think you know what to do. Okay, then there are some addressing integers, again the shader and the model matrix. What it is? The model matrix actually defines how the object would look in the scene, because program uses it to update these vertices of where should they be, how should these meshes look like, how it should be oriented and deformed also, probably, definitely. But it's very difficult to just define the final model matrix, and that's why we are using the matrix multiplication, and as I defined the model matrices in the presentation. As I said, I did not define them, they are defined. So we are using some attributes for position, rotation, scale, and color. You can use them to compute the final model matrix. And how to do that? Yes, we are going to get there. So our shape, it has some OpenGL filling the GPU with the buffers. Then the structure is deleting them. There are two functions, update and render. I'll get down to the beginning. So our code starts, or the program starts by the main function, which opens the window and starts its events. One of these events is on idle, as I said it last week, and it's called in the infinite loop, so it's doing something all the time. And this is the function we can use, and we are going to use for the animation. First, we define the color of the image or the scene. We delete it. Everything what was there is going away, because we are going to put there something new. We get the time as the parameter for the animation, and now we see that we have the objects created. We just want to tell them of how they should be animated. So yeah, here are the calls that would change the position, rotation, scale, shear, and whatever you need for your task. If you change them, then you call the update, because you're just changing the parameters, not the actual model matrix. The model matrix is changed, and should be changed, because it's not now, should be changed in the function update. So as you have your parameters set, now you use the matrix multiplication, you create the transformation matrices, and you just change the model matrix. How? By multiplication. You can try, play with it a little, and you'll see, you'll get the final answer. Then, as you have updated your model matrix, you changed the position of the objects, you want to render them. And the render function is actually calling the shader and OpenGL that uses the defined color of the image, the overall color, and its model matrix, because this is where the model matrix is used and how it changes the actual object. Finally, we see that you define the object as the triangles in the mesh, and there are 3, so you want to show them, you want to load them and view and then model this object as by triangles. So that's it. This is going in infinite loop. You are doing it, you are changing the animation in every iteration. And for me, there is just one thing to say, and that is good luck again.